All right, so we're going to kick it up a notch. Why does x need to be a function of t and y a function of t when we can make it a function of two variables, u and v? Or maybe later on, like r and theta, polar coordinates. Take a look at it. So now we can't do a total derivative with respect to u because it's just not a total, it's a partial derivative of z with respect to u. So d partial of z with respect to u is the partial of z with respect to x times the partial of x with respect to u. And then we've got the partial of z with respect to y times the partial of y with respect to u. We can do the same thing with v. Partial of z with respect to v is equal to the partial of z with respect to x times the partial of x with respect to v plus the partial of z with respect to y times the partial of y with respect to v. And of course, we can scale this up to three variables, x, y, and z. Those are the equations right there. All we've added is a partial of w with respect to z and times partial of z with respect to u, and then partial of z with respect to v. Nothing, it's just a little bit bigger. That's a good thing about switching to multivariable. Once you get the basic one down with two parts, it just upscales easily. I think it helps before we do an actual problem to take a look at like a tree you could use. So it helps to write trees. And all you're really doing is just follow the path. I go z, partial of z with respect to x, times the partial of x with respect to u, plus the partial of z with respect to x, times the partial of x. Oh, sorry. I'm doing in terms of u. So the partial of z with respect to x times the partial of x with respect to u, and the partial of z with respect to y times the partial of y with respect to u. When we do the v route, z with respect to x, x with respect to v, z with respect to y, y with respect to v. And the same thing happens up here. You follow the u, it's wx, if we're doing dw du, wx, and then xu plus wy, yu. So I'm using that nice subscript notation to speed this up a little bit, and then zu. Damn, that looks a lot better. I like that way better than showing all the partial derivative notations that we did up here. Look at me, learning something new every day. Unfortunately, none of the videos have that, but we'll use that in class. You just got to make sure you follow all the paths and just focus on the u's. So do all the u's first. And then when you're doing v's, do all the v's. All the paths that lead to v's. So that's a good way of using trees. That can help you keep track and not like screw up what everything is up here. God, I like that way better. Look at that. I could do this, or we could have that. Oh, this is so much prettier. We're going to start doing that in class. I like that. So let's take a look at an example. We're going to just do two parts here. So z is a function of x and y. X will be and y will be functions of u and v. We're going to do the partial. We're going to find both partials. So the partial of z with respect to u is partial of z with respect to x times dx du, or partial of x with respect to u. And then the partial of z with respect to y times the partial of y with respect to u. Notice that the partial of z with respect to x shows up in both, and the partial of z with respect to y shows up in both. You only need to calculate that once and just copy it from there. Use it. So I did the partial of z with respect to x. It's kind of nice and simple there. If we ignore the u and v for now, there's no product rule going on. It's each thing's got an individual thing, and the other variable's a constant at that point. So the partial of z with respect to x is e to the x sine y plus e to the y sine x. And the partial of z with respect to y is e to the x cosine y minus e to the y cosine x. So now we are going to insert in we'll make our dz, du, and dz, dv, or partial z with u and partial z with v. We need to plug in and use the partial of x with respect to u and v for these two, and the partial of y with respect to u and v for these two. So for both dz or the partial of z with respect to u and the partial of z with respect to v, I literally just took this bad boy and put it in both spots. I took this bad boy and put it right there, matching up with what we have up there. So the only really new thing I'm computing is this stuff right here. And we're just doing the derivatives with respect to u and v. So here, this is dx du, or partial of x with respect to u. The partial of x with respect to u is just 2u. While we're looking at x, we'll do the partial of x with respect to v. It's just 1. We plug in our y's. The partial of y with respect to u is just 1. And the partial of y with respect to v is just 2v. So we have these right here. I believe I said on the next page, but I'm going to say it here too. I would not plug in x equals u squared plus v into these things right here, nor would I plug in y equals u plus v squared into any of these things where y is here, unless specifically asked to do so. Because once you've got it in there, it might not be too bad in this problem. But in other problems where you see it all multiplied together, you can't go backwards very easy. So I would leave them separate for now and only put them in if you need to. Let's take a look at a bigger example. We'll use W with 3 parts now, X, Y, and Z. So W equals X to the 4th plus Y squared plus Z cubed minus 3XYZ. I've got X equals U squared V, Y equals UV, and Z equals UV squared. We're just going to look at the derivative of W with respect to U and the derivative of W with respect to V. Again, note these get repeated, so you only need to do them once. Okay? dV, the only part that changes is this part right here. Those are the parts we got to change when we do with respect to V. So let's go ahead and work it out. I got the partial of W with respect to X is 4x cubed minus 3yz. The partial of W with respect to Y is 2y minus 3xz. And the partial of W with respect to Z is 3z squared minus 3xy. We're going to plug those into our derivative with respect to U. So this is here. This is here. And I'll do a wavy line for this one. This one's right here. Now we're doing the derivative of each of these with respect to U. The partial of X with respect to U is 2uv. The partial of Y with respect to U is just V. And the partial of Z with respect to U is just V squared. Now we do the partial of W with respect to V. Again, recall these are just coming down. And now we're just looking at these with derivatives with respect to V now. Derivative of X with respect to V is U squared. The derivative of Y with respect to V is just U. And the derivative of Z with respect to V is 2uv. And I should have an equal sign in there, and I don't. Let's put that in there. And as I was saying, I would leave it as it is. Don't plug in U and V because it's kind of hard to go backwards at this point. if I plug in u squared v and uv squared for each of these x, y's, and z's, and I distribute these parts, I'm going to have something that I can't come back. I can't work backwards and check it very easily. So don't replace it unless you need to. And that'll be it for this section. Well, that video, at least. We got a couple more videos here. Peace.